The world-famous buildings of the Greek Isles, some less famous beetles, and the glaciers that, for now at least, dot the globe. Their common color, white, helps keep them all from heating up. Of all the colors, white absorbs the least amount of heat.
All right, so to solve these equations,
it's the color that Purdue University mechanical engineering professor Shulin Rowan thought could help with climate change.
The refractive index is going down.
Rowan and several of his students spent years on a quest to invent a new kind of white paint that could cool the planet.
You only need to paint less than 1% of the Earth's surface. No matter it's roofs, roads, cars, we should be able to totally reverse global warming and bring the temperature back to where we want it to be.
Commercial white paint is widely used in hotter climates because it reflects 80 to 90% of sunlight, which keeps surfaces from getting too hot. But Rowan wanted to take it a step further and figure out something that would actually cool surfaces.
So what our paint does, it reflects as high as 98.1% of sunlight, which means it only absorbs 1.9% of sunlight, almost no heat from the sun. Commercial white paints, they still absorb 10 to 20%. So in that sense, we cut the heat gained from the sun by 5 to 10 times. That's a big deal.
And that's enough to make the difference between something that cools itself and something that heats up.
Yeah, exactly.
One of Rowan's students, PhD candidate Joe Peoples, showed us what makes this paint different.
The particles have started to separate. You see how it's mixing?
It contains high concentrations of the chemical compound barium sulfite, which is used in cosmetics and to brighten photographic paper.
Many people think this is very dangerous. It's actually not. It's actually safe to ingest. So when you do medical x-rays of your bowels, you actually take barium sulfate. It makes your bowels opaque so that you can see them in the x-ray.
And how much paint are you going to make now?
This will make about 50 to 100 milliliters of paint. It takes around 18 hours, and that will cover around a 3 by 3 inch square.
To see one of those small, painstakingly painted copper squares in action, we went up to the rooftop.
This tile here is actually the brightest commercial white paint we can get. It has the most reflectivity of around 88%. And then this is our barium sulfate paint, which has a reflectivity of around 98.1%.
And just with the naked eye, this looks a brighter white
Correct.
than this. And actually, this is cool to the touch.
Already, yes. This one is absorbing so much more solar energy, therefore it's heating up. While this one is absorbing a little amount of solar energy, but it's rejecting more to deep space, so therefore we're getting it below ambient temperatures.
So it's actually cooling.
It's actually cooling. Just sitting here by itself with no electricity, it's cooling down below this outdoor temperature we feel now. Wow, they're about 10 degrees different right now.
To give us an idea of the difference the paint makes, Rowan and Peoples fired up an infrared thermometer.
What you can see here is this square is very orange,
right,
which means it's very warm compared to our paint, which is nice dark color, which means it's much, much cooler.
On this sunny 73-degree Fahrenheit day, the tile with their white paint was nearly 15 degrees cooler than the one with commercial paint, and more than 2 degrees cooler than the surrounding air. We were on top of the world's largest air conditioning research lab, something Rowan and Peoples hope the world will need less of with their paint.
Could this really eliminate the need for air conditioning?
I mean, it could eliminate air conditioning for certain locations and I would say certain time of the year. If you use this in Phoenix, Arizona or Reno, Nevada, it could save up to 75% of the cooling during the summer months.
Large-scale production would mean increased mining for barite, but Rowan says their paint is more environmentally friendly than commercial white paint. It took the researchers more than 7 years to test over 100 different materials before landing on this winning formula.
Tell me what it was like that moment or that day you realized you had succeeded, that this was actually cooling below ambient temperature.
As you can imagine, my PhD research was literally watching paint dry. So when we actually finally got something that was successful in what we theorized for so many years, it was extremely validating.
But I started to realize when we got so much interest from people all over the globe, we came to realize that many people need cooling in an affordable way. And in many places, aside from cooling, we need to address climate change. You know, our work can have a far-reaching impact than we thought.
They've applied for a patent for the formula and partnered with a major paint company in hopes of bringing it to the wider public. For the PBS NewsHour, I'm John Yang in West Lafayette, Indiana.